Chemical reactions and equations, chapter 8. It would be a good idea to read this chapter if you have trouble understanding it, okay? So, we're going to start with chemical equations. First of all, we have to know which are the reactants and which are the products, okay? So the reactants come when? First. Yeah, before the arrow. We just like to say that, before the arrow. So they come... Hold on, my thing's taking a while. Why is it taking so long to pull up drawing mode? There we go. Before the arrow, because they have to react, and the products come after the arrow. I know that seems very simplistic, but I have had kids ask me which ones are the reactants. Okay, the law of conservation of mass and energy, okay, has to be satisfied when we're doing chemical equations. In other words, remember the law of conservation of mass says that matter cannot be created or destroyed. Okay, so what that means for us is however many atoms we start with, we have to have the same number of atoms on the product side. Not arranged in the same way, but still the same total of numbers. So the example we did today, we found that on the other side we needed 2 chlorine and 2 hydrogen for the product side. Well, we didn't have that initially on the reactant side, so we had to balance that out. And that's why we balance, because we have to satisfy the law of conservation of mass. Okay? So same number of atoms of each element must appear on both sides of the equation. Yes?
Isn't it possible to like split atoms and...
Not in ordinary chemical reactions. So these are all for ordinary chemical reactions. Nuclear is a totally different field and it's totally different. So these are ordinary chemical reactions, which quite frankly are most of the things we deal with on a daily basis. Only if you're working in a nuclear plant or going to the sun are you dealing with some nuclear reactions. Okay? But yeah, that is a good point about nuclear. Okay, so the states of matter, we're usually going to indicate those when necessary. So I'm going to give you some, here in the next slide, I'm going to give you some things about the equation so that you can understand it. And that's what that big table is on your notes. Keep in mind our Brinkelhoff, okay? You always have to remember our Brinkelhoff. When you are writing them by themselves, they have to be like O2, H2, Cl2. Only when they are by themselves, okay? Only when they are by themselves. I can't stress that enough because people come show me a formula and they're like, but it's a Brinkelhoff, and they'll make it a 2 when it doesn't need to be a 2. Only when they are by themselves, okay? When we're talking about energy changes, all chemical changes are accompanied by a change in energy, okay? And that they're either going to be exothermic or endothermic, okay? So a reaction that releases energy, like the one we just did, got very what, Matthew? Hot. It got very, very hot. So that would be an exothermic reaction, okay? So exothermic reactions are releasing, so they feel hot. We would treat that as a product, okay? So if I was going to show that, I would go over to this equation and say plus heat, because it definitely gave off heat. It's probably still giving off heat, although notice that the bubbles have kind of stopped, okay? And that's probably because we have reacted all the HCl that was in there, and the liquid that's left is zinc chloride in an aqueous solution. There's no more active HCl. Okay, if a reaction absorbs energy, it's endothermic. Okay, and of the two, personally, I like endothermic better because they're cooler. Okay, so let's talk about some of the symbols. Okay, so we said in our equation when we're separating 2 or more reactants or products, like we did up there, we do a plus sign. That's going to separate them, okay? When I am writing a reaction, however, it does not matter whether I had done zinc plus HCl or if I had done HCl plus zinc. Doesn't matter which order you put it. We just did it that order because I added the zinc to the test tube first, okay? The yield sign is the arrow. I think Matthew had asked why we don't just put equal. I don't know, somewhere a long time ago they decided they'd do the yield sign, so it's going to that, okay? And it does not mean equal. We say yields or forms, okay? Sometimes we have reactions that are reversible, and we show that by a double-headed arrow. That means that the reaction can go back and forth, okay? If we have a reactant in its solid state, we would put a little S behind it. So for the reaction that we did today, we would have put a little S behind zinc to show that it was solid zinc, all right? An alternative to S we can sometimes use, but we only use this on the product side, and that's a down arrow. And that's for things that form a precipitate. And that just kind of shows, because if I have two liquids and I mix the two liquids together and I form a solid, what is that solid going to do? Is it going to stay floating, or is it going to fall down to the bottom? Fall down to the bottom. So that's where that arrow sometimes comes into play. So sometimes you'll see that. Okay? If we're indicating something that's a liquid, we're going to do a little L. And I do a cursive L, because if I just did a lowercase L, you're going to think it's a 1. So no, because that's what we use to designate liters. So we don't want to do that. Okay? So that indicates a liquid as a reactant or product. So for the HCl, we wouldn't have done L for liquid because it's not considered a liquid. It's considered aqueous, which we'll talk about in a second. Okay? So if something is aqueous, that's going to be AQ, which means dissolved in water. So that HCl that we did would have an AQ behind it because it's been dissolved in water. Okay? All acids are aqueous because it's the HCl, hydrogen chloride, that's been dissolved in water. Okay? If it's a gas, we use a little G. Okay? An alternative to gas, but only for when you have a gas as a product, is the up arrow. Because what just happened to the gas that we formed? It went up. We just happened to collect it in the tube that scared Matthew. Okay? If we had to add heat to a reaction, we are going to show that by we draw an arrow for our yields and we put a little triangle above it, and that just means in order for that to happen, we had to add heat to the reaction. A lot of times we'll show that when we're doing some decomposition reactions, because if I was to heat something up, sometimes I can decompose it, and so that just shows that we had to have heat. Okay? And then sometimes if something requires a catalyst, it'll have the arrow and then it might have like a little formula up there. And that would indicate that a catalyst was being used. Okay? And of course a catalyst is something that speeds up a reaction. You need to know that for a test, so underline that. Catalyst speeds up a reaction. We have catalysts in our body, but we call them something different. What do we call them? Enzymes. Okay? Same concept for chemical reactions. Sometimes we can put a catalyst in there and speed up a reaction. Okay? A lot of chemical plants use catalysts to speed up their reaction so they can make product in a quicker manner. Yes, sir.
What they said was that arrow?
MnO2. Yeah, MnO2. There are all kinds of catalysts out there. Sometimes it'll be a metal catalyst. My husband used to work at a plant that they used rhodium as a catalyst, which was elemental rhodium. And so it can be different things above there. That's just an example I used. Okay, so before we start actually trying to balance equation, I want to make sure we can all do an atom inventory or counting of the atoms. Okay, so we kind of touched on this when we were doing the reaction. So let's talk about the subscripts first. And you already know about the subscripts because that's how we wrote our formulas in our last two units. Okay, so the subscripts are the small numbers within a formula, and they tell you how many numbers are in the compound. Okay, they only go for what comes right before it. Okay, so for this magnesium chloride, that 2 is only for the chlorine. So that means I have 1 magnesium, 2 chlorine. Okay, I'm not going to spend much time on that because we've done that. I just want to also reiterate, if you've got a formula like this and you have the subscript outside, hopefully by now you realize that that means that 2 goes for everything inside, so that I would actually have 2 nitrogen and 6 oxygen. Remember, you multiply these two. Okay? So that's a quick review on that. But the coefficients are going to be the large numbers that we use to balance the equation with. Okay? And when you have a coefficient, it goes for everything that comes behind it. Okay? So in this case, it's cut off on my slide, but I think you can see it on your notes. You have a 3 right here. I don't know why. Well, it's cut off on this when it shows up. But there should be a 3 right there. Do y'all have that on your notes? Whoops. So, oh, come on. Ah. No. Stop. Technical difficulties today. Okay, that should have a 3 right there. Okay, so when I do this, that means I have 3 atoms of sodium. How many atoms of sulfur would I have? Oh, no, just kidding, I have 6. I didn't see that too. I have 6 atoms of sodium, 3 atoms of sulfur, and how many atoms of oxygen would I have? 12. Now you're getting the hang of it. And the next one, that should be a 4 right there. In front of that, I just can't see it on here, but y'all can.
It says,
Should it say CA?
sodium at the bottom.
Yeah, it should say, oh, on y'all's it does. On mine, I corrected it. Yeah, it should. So mark out sodium and put calcium. I literally just like copied and pasted when I was doing the notes, and I forgot to change that one. So calcium, so make sure you change that. How many calcium do I have? 12. How many phosphorus? 8. Because I have, this 2 goes for that, so I have 2 times 4 is 8. Now how many oxygen? There's a buttload.
32.
32. So I have to do this, 8 times 4 is 32. So now that you got the hang of that, okay, on this next, the ones down there, you can, oh, that's the next thing. I'm sorry, I looked ahead. Okay, so writing and balancing equation. So we talked about this with the demo. You first write your formulas correctly. Do not try to balance your equation until your formulas are written correctly, okay? On your worksheet today, one side is just balancing, so you're good there. But the other side, if you noticed, is you're going to write out the formulas, okay? And so this first part, we're just going to be writing. But when we get to the types of reactions, you're going to have to actually predict what it's making. And so you got to predict what it's making first, then balance, okay? But once you have your formulas written correctly, and you know they're correctly, you do not change anything in it. Do not change the subscripts. Do not change the formula. You have to balance using the big coefficients. I can't stress that enough. Okay? So, hints to balancing. Okay? I think I left you a little side thing that you can kind of write this down. A couple of things is, and you can find what works best for you. Okay? Usually I balance what I notice first. Okay, but there you can try to do metals first. Some people say do metals last, but for me, I would say metals first. Okay, if you can do metals first. The second thing I would do is, and this is very, very important, when you have polyatomic ions, remember those are those things in the parentheses, polyatomics, if they are, you treat them as one unit instead of breaking them apart into their individual polyatomic ions as one unit. And we'll do some examples of that in a minute. Because if you're breaking them down, let's say you have a nitrate, which is NO3, and you've got nitrates on both sides, if you're trying to break them down to nitrogen and oxygen, it makes it more complicated. Because if you'll just treat it as, oh, I've got 2 nitrates on both sides, then they're automatically balanced for you. Okay? And then if you have trouble, only if you're having trouble balancing, then go back and double check that you wrote your formulas correctly, okay? So check your formulas. Because sometimes you'll be thinking, I can't balance this, and you didn't write it correctly, okay? And then, of course, Brinkelhoff. Don't forget your Brinkelhoffs, because if you don't write it as a Brinkelhoff, you're going to balance it incorrectly, okay? Which will come to haunt you when we get to stoichiometry, because then you could have an incorrect mole ratio when we get to stoichiometry. Okay? All right, so let's practice. Whoops. All right, so this first one is the decomposition of water. I have H2O breaking down into hydrogen and oxygen gas. Okay? Hydrogen and oxygen by themselves have to have the H2. Okay? So what is the first thing you notice that's not balanced? Oxygen, okay? So oxygen is not balanced, okay? So the only way I can get oxygen to balance, because I have 2 here and only 1 here. So the only way I can change oxygen is to put a 2 in front of it right there, okay? So now I have 2 oxygen on both sides, but what did that do to hydrogen? It made it 4, so I got to fix that, and I got to put a 2 right here, okay? Now, when we don't have anything in front of it, it's a 1, okay? So when we're doing this on paper, you do not have to put the 1 there. But if you are having to enter things on Canvas, which you will while I'm gone, if it's blank, you need to go ahead and put the 1 in there, because I had to put blanks in there, so you've got to put the 1 in Canvas, okay? Everybody say that so you know.
Don't put the 1 in.
No, this is not time to do that. I'm not gonna be here to clarify your goofiness.
You gotta put the 1.
You gotta put the 1 in Canvas, okay? Because if you don't, it'll be counted wrong, and I don't wanna hear complaints when you say, I didn't tell you, because I just told you.
You didn't tell us.
Okay? All right. So this next one, this is an example of the nitrates, okay? I have a nitrate on both sides, okay? We are going to treat them as one unit, okay? So we can try our metals first, and currently our metals are balanced, so we're good. We've got a lead on each side, okay? But on the product side, I have 1 nitrate, and on the reactant side, I have 2 nitrates, okay? So there's only one way to fix that, and that is to put a big 2 in front of the sodium nitrate. Okay, so now these nitrates are balanced and this nitrate's balanced. But what did that do to sodium? It made 2 of them, so I need to put a 2 right here. Okay, so now I want to do a double check, and I want to say, okay, I have 1 lead on both sides, check. I have 2 sodium on both sides, check. And I have 2 NO3s on both sides, so check, it's balanced. Okay. Now, some people will say write all your elements down and do a little check on them. If you want to do that, that's fine, but then that takes you twice as long to balance. But some people will say, okay, on this side, I have carbon, hydrogen, and oxygen, and on this side, I have carbon, hydrogen, and oxygen, and then, okay, over here I have 4, over here I have 1, and you can do that if you want, okay? But most kids can just look at it, okay? Now, this last one is a special type. It's called combustion, which is the last type of reaction we'll learn when we start going through the types. But these are a little special, okay? I'm going to give you some hints of this when we get to it. But I want to show you this. If you look right here, oxygen is a -2, right? Not a -2, it has a 2 subscript, sorry, thinking charges. Has a 2 subscript. And anything multiplied by 2 is going to be what? Even or odd? Even. No matter what I multiply by 2, it's going to be even. Okay? Same thing with this 2 right here. Anything I put in front of there, it's going to stay an even number. But what about this water right here? I have a 1 oxygen there. Okay? I can't ever get things that are even to be odd, because no matter what I put in front of them, it's always going to be an even number. Do you agree with that? Okay? So here lies in the problem is that 1 oxygen. Okay? So my hint when you see these combustion type of problems, okay, and you'll know it's combustion by the always CO2 and water is your product. I go and I look right here at the hydrogen, okay, and on this one I'll balance hydrogen first. And if I look at that and once I figure out what I need to put in front of water, if it's an odd number, I don't proceed. I've got to do something different, okay, because if I put an odd number right here, I'm never going to get my oxygen to balance. Okay, because in here we will not use fractions. In AP Chem you can use fractions, but we're not using fractions in here. Okay, so what would I have to put in front of water right now to get my hydrogen to balance? A 5, odd number. Okay, so if I have to put an odd number in front of that, I go ahead and automatically I'll bump that one to 2. Okay, I'll automatically bump that one to 2. So now how many do I need to put in front of water to get hydrogen to balance? 10. Did you have a question or were you stretching? Okay. So now I put 10. Now I'm going to balance my carbon. When you're doing these types of reactions, always save oxygen for last. Okay. So now I have how many carbon? 8. So I'm going to put an 8 right here. Okay. So now I'm going to figure out how much total oxygen I have so that I can go balance it with the one on the reactant side. So I have 8 times 2 is 16 plus the 10 over here. So I have a total of 26 oxygen. So what am I going to need to put right here? 13. All right. Y'all are getting the hang of it. All right. So that's how you just straight out balance it. These are going to be practicing writing them out. So this is where knowing your pink sheets and knowing your ions is going to help. Okay? So in this case, iron, how do I write iron by itself?
Fe.
Fe. Oops. Oh, makes me so mad when I do that. Why isn't it going back to the other one? Oh my gosh, I'm having technical difficulties today. Let's just call it a day and all go home.
Okay. Yes.
No.
I'm doing it. They go back on us. Miss Parker told us to.
No, Miss Parker did not tell you to. It's a joke. Okay, iron is just Fe. Okay, here's where I want to caution you too, because this is what a lot of kids do, is they go look up iron and they see that it can have a +2 charge or a +3 charge, and they write it down that way. When it is completely by itself, it has no charge, okay, because it's in its elemental form, so it has no charge. It's not bonded with anything. So plus sulfur is just S, okay? And then it is telling us that we're making iron 2 sulfide. What does that Roman numeral mean again? It's a +2 charge. It's not telling us I have 2 iron. It's telling me that iron has a +2 charge. So iron's going to be a +2. And what is sulfide when it's in a compound? It's group 16. Everything in group 16 is a -2. So that's a -2. So it would just go together like this. And that's one of the fun ones because it's already balanced. Okay, everything's one of everything on both sides, so we're good. Okay, next one is zinc. Earlier, Abby was so kind to tell us that zinc is Zn because it's metal plus copper 2 sulfate. Who wants to tell me how to write that? Copper 2 means it's a +2. You're going to need your pink sheets, people. CuSO4. Very good. Okay? And it's making zinc sulfate plus copper. Okay? So zinc, we said earlier, was a +2, so then this would be zinc sulfate plus copper. Okay? Again, copper by itself is, when it's all by itself, it's just Cu. There's no charge. So this one is also already balanced. Okay? We like those. We like those. Okay? Here we go. I'm going to remember to hit the pen that I need to write. Silver nitrate, AgNO3, plus sodium bromide is NaBr. And then on the other side we get silver bromide, which is AgBr, plus sodium nitrate, NaNO3. Another one that's already balanced, because everything in there either has a +1 or a -1 charge. Okay? And then let's do this last one, and then we are done. Ferric, y'all don't know what that means. I'm going to tell you it means the iron 3. Okay? So I have FeCl3, because iron's a +3, chlorine's a -1, plus ammonium hydroxide, which is OH. That's an O. And that's going to make iron 3 hydroxide. Hydroxide's a -1, so we would have FeOH3 plus ammonium chloride. This one is going to need to be balanced. What's the first thing you notice, Hayden?
First thing I noticed?
Mm-hmm. Chlorine. Chlorine's not balanced, okay? So you notice that because it has 3 chlorine on the reactant side right here and only 1 over here. So how could we fix that?
Like,
We need 2 more over there.
Well, what do I want to put in front of this whole compound? 3. So I put a 3 in front. I cannot change the subscript, so I have to put a 3 in front. Okay, but now what did that do to my ammonium? It made it, no, it made ammonium 3. Remember ammonium? Remember ammonium is NH4+. It's a polyatomic. Okay? So if that made that 3, I only have 1 ammonium over here. So how would I fix that? Put a 3, and then look what that did for my hydroxide.
it made 3 of them.
It made 3 and 3, so now it's balanced. Okay? All right? So that's why it's just best to start with what you notice first, because a lot of times when you start with that, it ends up balancing the other stuff for you. Okay? And that is the end.